Hello students, welcome to Edison. This video we are going to discuss about Dijkstra algorithm. Till date we have completed the graph introduction and also how the searching technique or traversing techniques are being done. That also we have discussed. Which data structure is really helpful for us. That also we have discussed. And in the previous videos also we recently covered shortest path. Uh, or why it is needed also we discussed, spanning tree, minimum spanning tree, and also to find out minimum spanning tree we have recently studied Kruskal algorithm and Prim's algorithm. So now it's not about to find any MST. Dijkstra algorithm we are using to find the minimum cost. You can say the better example for it is, so you are starting your journey from your home to any other location. Let us take you are moving for a party or something. You know there are many hubs or you can say squares you need to go through, or might be many different locations which are known locations for you. You just keep in mind, like always we are thinking to reach to the destination within less amount of time or less amount of distance. If distance is less, definitely we will reach within time. So that is why we are actually finding the least cost, or you can say the less amount we are trying to, or less distance we are trying to cover from one into another. So that's why it is also named as single source shortest path. Means the source will be single. Okay, the single source, any source might be your home or might be any locations. If whatever the destination with the different nodes that you are actually collecting, suppose this is your destination, this is from single source. You started your journey and anyway you found a shortest path. This is what the approach or the applicability of Dijkstra's algorithm. That is why we are saying it is single source shortest path. We are finding the shortest path. Whichever we have checked, suppose we are going for finding shortest one. So there are possible directions in future. We will be discussing that one in an example. So all edges are connected. Our target is the minimum will be picked. That's why we are picking the minimum. We are not thinking of what will be the next. We are only focusing on the minimum one. That is what a greedy approach is. The difference between greedy and dynamic is, kindly check the introductory video there I discussed well. Still, though it's a part of greedy, so I'm just discussing with a few words. You can say greedy and DP. The main uh, difference is the memory. We are not using memory in DP, dynamic programming. We are using memory in dynamic programming, but not in greedy approach. Though we are not using any memory in greedy approach, that's why we set a condition only. Through the condition, it has to keep. So, though through the condition, it may not be always having probability 1, means it is not able to provide the optimal solution always. That is why we are following the dynamic programming. In dynamic programming, we are keeping all the paths or all the distances from source to destination in a single table. Like there are also methods, tabulation method, memorization method also there. We will be discussing that one later onwards. But we have to store the values. Out of the values which we stored from source to destination path, the minimum will be picked. So definitely probabilities is, you can say probability is 1. The 100% accuracy is there, but it will take time. That's why we are focusing on greedy approach. This is the detailed video is there in an introductory video. Introduction video is the first video of this series. You can check that one. I totally discuss how it is working with a proper example. Now we'll go for the digester algorithm. So once again, I'm telling you this approach, this algorithm which I kept here is the approach of Corman. There are other algorithms too you can find in Tado's book also. Always follow the book because in the book it is clearly mentioned everything. Rather than reading from the videos or any internet stuff, it's my a request, a suggestion you can say, you can start reading the book. From the book, at least it could be very much easy or convenient for you to understand it. If you're not getting it, you can check the video, not an issue. But at least before reading, before watching the video, at least reading the book. Okay, it's mandatory. Basically, 100% knowledge you'll get from the book. Okay, now this is a Dijkstra algorithm. So Dijkstra function or Dijkstra function, you can say it's written. G stands for the graph, W stands for the cost or the weight, okay, and A stands for the source vertex. We will be starting from a source, definitely. It is single source shortest path. I'm just writing it. Single source shortest path means source will be single, path will be shortest. Okay, destination will have only one to one destinations. We have to reach many destinations in between. So we will be keeping the distance within the node that we will be discussing in the exam. The next part is the example that I kept for you to for the better understanding of it. So first, what we have to do is we have to initialize. First, we have to initialize. Again, an approach we are using here is a function we are using. So this function I kept again from the core main. So here it is saying initializing single source. First G, the graph we have decided, and small s represents the source vertex only. Okay. Here we are running the for loop. Small v belongs to all the vertices of the graph. Okay. And this D stands for the distance. Initially we are saying infinity to all the vertices, okay, excluding the source vertex. All the distances, let us assume as infinity is not by the way represented in computer science. You can say it's a huge number could be 1000 or 2000 or 3000. Certain value we have to keep which is more than the value which might be expected. Suppose you are expecting maximum value could be 20,000 or 30,000, so just increase that one would be considered as the infinity. Okay, so next is this pi represents the predecessor of it. Whatever the value that you kept, okay, the previous value you have to keep. So this time I don't think this pi we will keep because it's a by default a predecessor of it. The predecessor knows its requirement here, but it would be requirement. It would be a part of requirement whenever you are going for relaxing the nodes. That time we will discuss that one. Okay. So now we what we have to do? We have to just making the distance of the source as zero. Others will be infinity or infinite or a use value. We can let us take for the example first. Next, the capital S will keep the vertices, the minimum vertices we can say, the proper distance in different word I can say. It keeps the selected uh, extracted minimum value. Okay, that we will discuss now. Next line here q we are taking which is the vertices of the graph. Okay, all the vertices of graph we have taken. Now we are running a loop where the condition is given until it is empty. We have to find out the minimum first. The fifth line says until it is empty means the queue which is a total number of vertices we first have to collect it. So we have to pick one by one and we have to reduce that one and we have to go for until it is empty. We want to run the loop. So the first u is extract main from q. The vertices which we have we have to pick the minimum one. How it is running, don't worry, we will be discussing that one through the example. Okay, next capital S, once we have selected the small u, that we are taking the union means we are adding to it. Okay, next for loop is running through which we have to check the small v belongs to the adjacency. That adjacent thing we are using, that is why pi is getting used. So it is a predecessor or a parent node to it. So that is what we discussed in previous videos too. Next is relax. This term you should have to remember because this will help you to run the Dijkstra algorithm. So relax, here the source vertex, destination vertex, and the cost or a weight of that edge. Okay. Condition is if v dot d means distance of the destination is greater than uh, you can say source distance of the source plus cost of the edge connected to the vertices. If such condition will happen, you can say you have to initialize, you have to update the value of the v or the distance will be updated as distance of the source plus cost or the weight assigned to that edge connected to the two vertices, and we can say it's a predecessor of u. Okay, so don't worry, now we'll go for the example. From this you can expect, though we are using priority queue, so through this priority queue you can say the time complexity could be, it's uh, directly I'll write e log v, or else I'm just putting within this. Okay, or else sometimes we can say it's big of v plus e log v also we are saying. Why? Because the first is this initialization you are using, which is v that you have taken, though e log v is greater than it, that is why we are just saying it's a value, but sometimes we can represent in this way if you are using priority queue. If you are using priority queue, if you are not using priority queue, so in the previous Prim's algorithm also we discussed that one. So if you're not using it, it could be represented as v square, or it could be represented as n square, where n and v both are called as vertex. Okay, vertex of graph G. This is what a complexity we found. Next, also the example. Again, I'm telling you, this is a detailed video. So in detailed video, I'm keeping all the information of the book, and I try to tell you in such a way that it would be understood by you. Okay. In the problem solving video, we will run our approach to tackle the problem. Okay. So as for the first initialization, initialization is we have to keep the first vertex as 0 first. I'm just writing my steps which will be very much convenient for you to understand. Any vertex will be selected as the source vertex. Once we are selecting that one, making the source vertex distance as 0. Okay, any vertex which is selected as source vertex, any vertex which is selected as source vertex, then initialize the value, or you can say initialize the distance as 0. Any vertex which is selected as source vertex, initialize the distance as 0. Then initialize the distance as 0. Why? Because source to source means wherever you are standing, from that end to, means again you are standing, means your no distance that you have covered. You are only standing. So the you are sitting here. So that's why we say it's a 0. And next, and update, or you can say and assign infinity as distance of other, you can say vertices, and assign infinity as distance of other vertices. Clear? So what exactly we have to do? We have to take the source vertex, clear, source vertex, and then initialize the distance as 0 and assign infinity as distance of other vertices. Okay. Once it is done, so here as per this example, the first one, this is A. Okay, this is first step. As we have gone for, as we have gone for 0, so this is our source vertex. Clear? So though we selected this as source vertex, first the value will be assigned as 0 and others are assigned as infinity. But in theoretical this is possible, but in practical what we have to do, we have to just keep the maximum value to it. Okay, we have to go for the maximum value. Next thing is the connected vertex or vertices will be relaxed. Okay, relaxed first. Then formula for relaxation is, means we are making it free. That is why we are saying the term is relaxation or relax. Okay, so what we have to do is distance, if I should write it, if distance of distance of destination vertex, if distance of what destination vertex is greater than distance of source vertex plus cost or weight assigned to both the vertices. Okay, so this is what, like if the distance is greater than distance of the destination vertex is greater than the distance of source vertex plus cost and weight assigned to both the vertices, then what we have to say, we have to write it better. Distance will be distance of destination vertex will be equal to distance of source vertex plus cost or weight assigned to both the vertices. Clear? This will be updated. This is what the relaxation procedure is. Don't worry, now we will be discussing it. So we, as for the initialization, we have to put 0 with the source vertex. Next, others will be considered as infinity, means a greater value will be assigned. Next, for when we will go for the relaxation, the connected will be relaxed. Clear? Connected will be relaxed, but based on the condition. So here it is considered as V as per the relaxation term. I can say it's V, small v, but I'll discuss with the small v, and this is small u. Okay. So small v, here we will discuss. Small v distance is now infinity. Okay. So this is the distance of small v. This is the distance of small u, which is 0. Why? Because it is a source now, and other will be considered as the destination. Okay. Next, we are running the if condition. If v of, or the distance v dot d, the distance of this one is, and this part is weight of u comma v. Okay. This is what we have to be considering. Next is weight assigned to that age. Clear? So in this case, you can say it is infinity. Infinity is greater than, the distance is 0 plus the 10. Clear now? Infinity is greater than 10. Definitely it is possible. So if condition satisfies, means the the distance of the destination is more than the addition of the source distance with the age. Clear? We will say it will be updating or it will be relaxed. So in other words, you can say यदि ये बड़ा हो रहा है, ऑलवेज थिंक इन माइंड, ज्यादा बड़ा हो रहा है तो हमें ढूंढना क्या है, हमें छोटा ढूंढना है. क्लियर? हमें और छोटा नहीं है तो अपडेट कर लो. So that is why what we are doing, we are updating this vd with ud plus w of ud. So that is what we are doing. So vd indirectly will be 10. So इसीलिए यहाँ पे 10 अपडेट हो गया है. ठीक है? That is why it is getting updated. Clear? So for this case also, it was previously infinity. So here you can say it's u and this is v. For this it is ub. Clear? So in this case also, we can say it will be updated because infinity is greater than 5 plus 0. Or you can say better, I will write destination with this one. So infinity is greater than 5. So better the 5 will be updated. You need to relax it. Once it is done, out of two you can pick anything, but in general sense, we are trying to go for the lowest one. Why? Because it is written here. Okay, extract mean, you are going for the extracting the minimum one. That is why we will start from it. Okay. So 10 and 5 and others are infinity, so we are not going for the infinity directly. Okay. We start with the lowest one with the relaxed. Clear? Which are the value we got. Once it is done, we say it is relaxed and we color it black. Okay. Now whenever we are going for the processing, so that is gray. Inside the book it is clearly mentioned. If it is in a process, we are keeping the color as gray, and once it is done its work, we say it's black. Once it is not yet done, anything is not getting updated, we say it's white, the background is white. Here it is clearly represented. Now we are keeping y as our source right now. Clear? Whenever we are saying it is source, what we have to do is u of d, you can check of, for the timing you can say it is v now. For this case, clear? I'm just writing here. For this case, I have to check whether v dot d is greater than, if v dot d is greater than u dot d plus w u comma v. Clear na? So in this case we have to check if condition 10 is greater than 5 plus 3 or not, because this is connecting this u and v. Clear? So here we can say yes, 10 is greater than 8. If it is, then we update that as 8. So here 8 is written. Clear? So like that, there are also the values. Previously it was infinity. Infinity is greater than 5 plus 9. So it's 14, no? So that will be updated as 14 using this link. Clear? Using this link, we can update the value as 14. Next, Z is connected. You can say previously it was infinity. So infinity plus 2, infinity is greater than, the distance here is 5 and the age it is connected is 2. So infinity is greater than 7. If yes, then update that as the value which you got as raise 1. So here they have updated it, and though we have done its work, no need to update it further, though our work is over now. Clear? So we can say we have relaxed the node. Like this, you can say, though we have relaxed it. So here this is a process. We started a process. Now it says U for us. For the timing, you can say there is the connection from this end to that end. But though we started from S, we will never change the value. You remember. Or else if you think, no, we can change. Not an issue. You check now. This is U and this is V. So for the d of v or vd, you can say whether it is greater than, this or not. W u comma v means it is the value of v is 0, and the cost here is 7 and here is 7. Whether 0 is greater than 14 or not? No, no. If it is greater than, if it is less than 14, definitely you can update it. It's not less than 14. So we are not going to update it. That's why I told you the source we started, it's better we should remove that one for a while, because though it is connected in future somewhere we have a link, so we have to avoid that because we are started from the source. Now you can say up to this whatever we completed, now you can say if we start from S, the minimum distance for this is 5, because from this path if we follow, the minimum actually we can expect. If you can say from this end to that end, we can it can be possible to reach, not an issue. But is it providing the minimum? No. 10 plus 2 is 12. That is why we cannot expect the minimum one from this end. So this is how we can say source is single, but destination could be multiple, not an issue. Destination could be multiple, but source should be single. So it is single source shortest path. Okay. So now you can say, though we started from U as this, only one point and second point, though we started with this one, so it's not possible for our end. Now X could be relaxed, like Z could be relaxed using this age. So now you can say 7 plus 14 is greater than 7 plus 6 or not. 7 plus 6, definitely it will be updated. So you can change the value because 14 is greater than 13, so definitely we will update it. So we update it, update the value and make it relaxed. Means from this end no connection could be established. So one time relaxation is been done in Dijkstra algorithm. Okay. Next, the minimum. Out of this 8 and 3, the minimum that we know is 8. That is why we started from 8. Okay. Now, you can say here it's U. This side also connection is there. If you think this is V for you, so dv is 5. Whether 5 is greater than 8 plus 2 or not. 5 is greater than 10. No, no. So that's why we are not going to update that one. And also one more thing you remember, once a node is getting relaxed, we are not going to relax that once again, because one time relaxation is done in Dijkstra algorithm. Okay. That is why in future the problem you may face, that I'll also discuss. Next is, you can say here if I say it's a V, can it be replaced? 13 is greater than 8, the cost of the source plus the weight assigned to the age. 13 is greater than 9, then update it. Then update it, not an issue. So it is now updated here, 9, and T is relaxed. Okay. Now from T, is there any other options we have to find? Like suppose this is U and this is V, because no other connections we can expect for this. The 7 is not greater than 9 plus 4. 9 plus 4. Though it is not greater than, so no need to relax it. That is why we can say every node has been relaxed properly until it is relaxed. So I must say third point, repeat step 2 until all nodes or vertices have relaxed. Until all have been relaxed, we have to run it. Okay, this is the approach you must remember. The smallest we are picking as our next source. Okay, next out of this updation we found 7, 8, 14. So 7 is the lowest, that is why we started with that. So you please remember that one. This is how we are actually running using this Gorman method. And one more thing I have to tell you before the application, I should have to tell where it fails. Where, okay, where Dijkstra's algorithm fails, you can say better example from A to B. Then suppose you can say D is getting added. Small example could be better for us to understand. Clear? From this end, you can say -2. Mm, that could be better if you can say mm, let us take this is 2, this is 1. Okay, this is 1 and this is 2. So if you want to relax it, as per the example what we have to do, as per the Dijkstra, we have to relax all the nodes first. How it is getting connected first we have to check. Though we started from the source A, source will be set as 0. I'm just changing the color. It's 0 and others will be considered as infinity. Yeah, this is A, this is B and this is C. Okay, next what we have to do, we have to update the values. Okay, we have to update the value based on the U and V concept. Here you can say suppose this is 1 and this is 2, this is 2, this is 1. I'm just changing the example, just a little bit idea that I put. I thought it could be a better option for us to decide now. Okay, so the step 1 is this one. Okay, this is step 1. As for it, we are going to initialize it. Next in step 2 what we have to do, 2 1 minus 2, here is A, B, C. What we have to do is we have to check the updation. Here the value was 0. Okay, I'm just changing the color now. The value was 0. It was previously infinity. Whether infinity is greater than the distance plus the cost. Infinity is greater than 1. If yes, then you can say 1 will be updated now. Clear? Here also in this case we say infinity is greater than 0 plus 2, the age. Okay, so infinity is greater than 2, so this is okay. So definitely you can put the value as 2. Now though it is relaxed, I must say, I must highlight it, and I say this highlight is said to be relaxed. This set relaxed. Okay, this color set we have done the relaxation. From this end, relaxation has been done. Now you can go for step 3. In step 3, the same diagram you draw with the proper relaxation. Okay, so here the value I should write a b c 2 minus 2. Here it is 1, 0, 1, 2. Okay, next is, though it was already relaxed, now our term is out of this 2, we have this and this option to get the relaxation. Until it will relax, we have to run the Dijkstra approach, a Dijkstra algorithm. Here what happens, it like the minimum will be selected for relaxation. We are selecting this one. Why? Because it is minimum for us out of this 2. So for this we found no, nothing is connected, like not, no out degree is there from B. So that's why we can say, though no out degree is connected, we can say it is relaxed. As I told you, it will relax for one time, though in future there are many paths connected to the relaxed one, so we will not able to relax. Just one time relaxation is done in algorithm. This is digest algorithm. This is already been defined well, so as in the book, clear. Next is in step 4, what we have to check is a b c, and this is 2, this is 1, and this is minus 2. The value I'm writing as 0, this is 1, and this is 2. Okay, it has already been relaxed, it is already relaxed. Now it's time to relax the C now. Okay, so the C, okay, here if you say this is U, this is V for the timing, for this condition, V D should be, if it is greater than U D plus cost or weight of U comma V. Clear? Means if condition, the distance of V is this one. Okay, 1 is greater than 2 plus minus 2. Okay, 2 minus 2, this part will be considered as 0 now. I'm just writing here, if 1 0, yes, possible hai, theek hai, correct hai. But though it is already relaxed, we will not able to relax it further. So the problem it occurs is, one time relaxation is done for this approach. That's why we can say it is relaxed and we cannot do further. But it is a wrong answer. Clear? So we know, as for this, we can select this path. If we select this path, the distance could be set as 0, but this is not practically possible. We can say some negative distance we can expect, or some lesser value we are expecting out of it. But it is not exactly giving us the correct result. Okay, so negative distance is not possible, by the way, but still, in a you can say, as for this graph, we can write it theoretically. So the problem we found is, I'm just writing the note, Dijkstra algorithm relaxation is done for only one time in Dijkstra's algorithm. If one time relaxation is done, no further relaxation could be expected. Here, negative weighted age may or may not work in Dijkstra algorithm. You can ask me, sir, may or may not? Why? You can check. Instead of this one, if you can say, the value could be something like you can say, it is 10. No? It is 10. You can say, now it is, for the timing, you can say it's 11. Clear? Suppose such thing happened. Then what you have to check is 10 will be there, 11 this side, not an issue. If 11 this side, so we can expect 9, but 10 is already being done. Means the less value, if you say previously, here the less value we have given, that's why we can say it's relaxed first. Suppose you can say instead of 2, instead of 1, I'm just putting it 3. So if I'm putting it 3, so 2 will be relaxed first. If 2 will be relaxed, it will be given as 0. Clear? From 0, no connection is there, so it may or may not. Clear? So may or may not condition could be appeared due to this condition. Here, uh, out of this condition, we can have to relax. If I'll go for the relaxation, I can write it 3. Okay. If I'll write it 3, so the problem could be the 3 we will not relax because 2 will be written here inside. So 2 will be getting relaxed. So 2, the connection is there. So definitely we can relax through minus 2 is 0. Once we'll do the 0 now, so it will be a probability definitely will get the correct answer. But it's not always possible. Sometimes we may or may not get the proper answer. That is why we say it may or may not work for this condition. Clear? Now let us think. Suppose you have updated as 1 and this value is now 3. Okay. 3, then it is updated as 3 minus 2 is 1, also the same value. You can do that, but negative edge may or may not work. But maximum time we have seen it is not working. Okay, that is why I have written the answer as a note here. You remember this thing. But before that, we should go for the application where we can apply. In Google Maps it is getting used, or finding shortest path, or you can say geographical map, which is equivalent to the Google Maps basically. And you can say IP routing, whenever you'll read in networking, the routing like the nearest hub or nearest switch, or else you can say whenever you are finding the cellular tower. Suppose you are in a journey, you are actually in a train, suppose. So you know it's a 200 kilometer per hour the speed is. So that time whichever is nearer, that it will connect immediately. So this is we are using whenever we are finding the path, or whenever we are trying to connect with the nearest cell tower. You are talking through phone and the train speed is around 120 kilometer per hour, suppose. In that case, it's a speed of train may vary, but the connection will be established fast, or faster connection is to be needed. So if nearer tower will get, so definitely it connect, or else if some far connection it is being needed, that time the call get disconnected whenever you are on a journey and you are talking that time. So this is because of the problem, the nearest could not be found properly. That is what it has been done. Also in telephoning network, which we discussed now, and distance between the locations we can definitely find out. and filing locations refers to the vertices of a graph. So these are the applications of it. So the note you should remember, relaxation will be done for one time and negative weight age may or may not work in Dijkstra's algorithm. I think it is clearly understood by you. If any problem, you may comment below. And thank you for watching. Have a good day.